Hello students. So in today's video we are going to discuss the theory and applications related to the concept of reduced mass. Reduced mass is slightly tricky a topic, but once you understand it well, you will see that how you can use it to solve some of your problems in quite an easier way. Okay, so let's proceed. So what is reduced mass first of all? Reduced mass essentially is the effective mass, effective single mass that we can use in place of a two mass system in order to study those masses. Okay. So as you can see here in this figure, we have this two mass system which are somehow connected to each other. They might not be physically connected, but there would be some interaction between them, whether it is internal because of some forces that they are exerting on each other, or maybe they are bound in some way. And as we try to study the motion of such blocks or bodies, two bodies together, we say that we can reduce this two mass system into one single mass, and then we just have to study that one mass system. And all of you must agree that studying a single mass system would be much easier than studying a double mass system or two mass system, and hence we say that using the reduced mass concept simplifies some of our problems to a great extent. So today we shall talk about all those things, and mathematically if we check the value of the reduced mass, that single mass that we have to use in place of the two masses is given by this formula. Mu, which we call as the reduced mass, is given by m1 m2 by m1 plus m2, where m1 and m2 are the two masses in under study. So as we proceed, one of the major things that where we use the reduced mass is in the process of determining the kinetic energy of a two mass system. As you can see, we have here two masses m1 and m2, which are, let us say, moving with speeds v1 and v2. When we try and define the kinetic energy of these two masses system, the basic definition for the total kinetic energy of this system would be the kinetic energy of the individual masses, and then you just add that. Yes. Now we say that there is one more way in which we can define this kinetic energy if we want to use the reduced mass of the system, and that is by writing this kinetic energy in some other way. Now what is that way? Maybe I will tell you, and then I'll tell you how we get this expression that I have written next. So see that for these two masses, I can write their kinetic energy as the kinetic energy of the center of mass of this system, which will be the total mass times the velocity of the center of mass and square of that. This will be the first term for the kinetic energy, and then consider the next terms to be something like the kinetic energy of these two particles with respect to the center of mass. So it will be like kinetic energy of m1 with respect to center of mass plus the kinetic energy of m2 with respect to center of mass, which if you understand will have terms like this. First term will be like half m1 into velocity of mass m1 with respect to the center of mass, which will be something like v1 minus vcm, yes, whole squared of that. And the second term similarly will be something like half m2 into v2 minus vcm whole squared, where if you just substitute the values of vcm, we all know how to find out the value of center of mass of such a system. We know that vcm is given by m1 v1 plus m2 v2 over m1 plus m2. So in this case, when we substitute this value of vcm over these in these two expressions and then solve them, we will see that we will get terms like this. This is the first term that I have just written above here as well. Whereas the second term that we have got here is upon solving these two terms. You can just do that as a small exercise separately. I have just directly written the result here. And if you just check the second term, it tells you that there is this term coming up here, which we have now written as mu in the last expression, and this v1 minus v2 whole squared we are calling as v relative. So what we say here is that this kinetic energy of this system, the total kinetic energy, can also be written like the kinetic energy of the center of mass of the system plus the kinetic energy of the reduced mass, where you consider the reduced mass to be moving with the speed of v1 minus v2, the relative speed of the two particles. So, once we understand that the kinetic energy of this two mass system can be written in this form, we shall see that as we use this into various questions, it helps us simplify the problems a bit too much. It is only this one expression that you need to keep in mind. This might look a little tedious initially, but as you work through the problems, as we check, as we see problems related to this, you will see how simple it is to apply it to the problems. So, next we move on to the applications directly. So, the very first application that you find for a reduced mass system is in finding out the moment of inertia of a two mass system about an axis which passes through the center of mass. So, here we have drawn the figure. There are two masses separated by a distance r, and if we try to find out the moment of inertia of this system about an axis passing through the center of mass, it will be m1 r1 squared by definition plus m2 into r2 squared, where you know how r1 and r2 are related to r, the total distance between them. This we already know from the concept of center of mass. r1 you understand will be given by m2 by m1 plus m2 times capital R, and r2 will be given by m1 by m1 plus m2 times capital R. Yes. Now, if we just substitute these values of r1 and r2 over here in these two terms, we can easily prove that the same moment of inertia will come out to be mu times capital R squared. So, it actually turns out to be like this: m1 m2 over m1 plus m2 times capital R square. There is a little bit of calculation that goes into it. You can just try this out and check for yourself that the moment of inertia of this system of two particles can be written in terms of its reduced mass, which we can now consider to be at a distance r from the axis of rotation. Okay, so, you can directly use this term for the moment of inertia of the system of two masses. The second application comes in a system where you have two blocks which are attached together with a spring, and let us say the blocks are given some initial velocities v1 and v2 as it has been shown here in the figure, and the question asks you to find out, let us say, the maximum elongation or the maximum compression in the spring as a result of this movement that you have provided to the blocks. So, if you go by the usual method, what is the procedure that you follow for such questions? You first consider the two blocks to be connected together with a spring which is which creates a force which is conservative in nature. So, that you can say that the total energy of this system will be always conserved. Apart from that, if you consider both the masses as a single system, you say that there is no external force on the system, so that the total momentum of the system will remain conserved. So, and the third condition then, which is the condition for the spring to have maximum extension of or maximum compression, you say that for that it will happen at the moment when the two blocks are moving with one single velocity, with a common velocity. Yes. So, it is these three things that we have to take together, prepare equations, one equation for law of conservation of momentum, the other equation for law of conservation of energy, and within those equations you will use this condition that the relative velocity of the two blocks becomes 0 when the spring is in its maximum extension or maximum compression state, right. We will see now that how can we reduce this two equation problem to a single equation problem if we can just work using the reduced mass system. Okay. So, one thing that we observe here is that the external force on this system is 0. Yes, it is only the spring force which is acting, which we can consider as an internal force if we consider both the masses as a single system, which means that the velocity of the center of mass of this system will remain a constant. Yes. Now, once we know this, now when we try to directly conserve the energy of this system in this initial state that we have shown here in the figure, and the state when the spring will have maximum elongation or maximum compression depending upon which one out of V1 and V2 is greater, See that we will get our answer in one single equation. That will solve us a lot of time. So, as we try to write the equation for conservation of energy principle implies the initial kinetic energy of the system, which is half capital M here is the total mass of the system, times VCM squared. This is the first term of the kinetic energy written for the two blocks together. I am using this expression here to write the kinetic energy, plus the second term will be half mu, the reduced mass, times V1 minus V2 whole squared, right. See that there will be no potential energy in the system here, because initially the spring is in its natural length. Now, I am sorry. Now, when we try to write the final energy of the system, where you see that when the system is in most compressed or most elongated state, and if we assume that that stretch in the spring is x, we understand that there will be a potential energy in the system half kx squared plus the kinetic energy of the system. We can once again write in the same form, in the form of these two terms. One is, the first term will be half capital M into VCM squared. Now, understand that this particular term will be the same as this first term here, because we know that VCM is a constant throughout, it is not changing. Plus the second term here will be half mu into V1 minus V2, which will be now the relative velocity finally, and we know that this is going to be 0, because we know that at the state with where we are writing this energy here, the two blocks are moving together with the common velocity. So, this V relative here will come out to be 0, and see what is happening now. So, these two terms cancel out, this term is anyway 0, you get your answer in this one single equation. Do you see that? You are supposed to find out x, where you know everything else except for x, and you can just solve this equation and get your answer. Okay. So, see that how without using the law of conservation of momentum, you are able to solve this question easily by using the reduced mass concept. Now, the important thing here is, once you understand that in all questions where there is no external force acting on the system, the velocity of center of mass remains a constant, you automatically know that you can always do away with this term in the kinetic energy expression. From now on, when we start using this expression for kinetic energy, knowing that this particular term half capital M VCM squared is going to be a common term on both the sides, we can simply delete it. We just do not consider it while writing the equations now. That can be done. And if you want, you can take this as some kind of writing the kinetic energy in the frame of the center of mass, which makes VCM itself 0, right. If you want to physically, you can consider it to be a case like that as well. So, this is one important application of reduced mass system. So, let us see one more question based upon this, just to have a fair idea. So, this time we have the two blocks M1 and M2 connected with a spring of constant k and being given initial velocities V1 and V2, which are this time in the opposite directions. Okay. And you are supposed to find out the same thing. This time we are sure that there will be a maximum elongation in the spring initially, and that will happen when both the blocks will have one single velocity, one common velocity. The question also asks you to find out the time period of oscillation of the two masses. So, we will discuss that also. So, this time when we try to write the similar equation that we have written above, conservation of energy, where you will write the kinetic energy, initial kinetic energy, which will be half capital M into VCM squared. This time I can just remove this step, this particular term here itself, because I know that it is going to get cancelled on the other side, plus half mu into V relative. If you just look at the figure carefully, it is V1 plus V2 this time, because the two velocities are in the opposite direction, is equal to at the moment of maximum elongation, we know that the extension in the spring will be, if it is x, then the potential energy in the spring will be half kx squared plus the kinetic energy of the system in that state, which I can once again write as half capital M into VCM squared, which is getting cancelled with the term on the left, plus half mu into V relative. Once again, this is going to be 0 at the point of maximum elongation. So, this term goes to 0, half m VCM squared is already 0. So, you get the value of maximum elongation just by solving this one equation. Okay. The second part of the question, to find out the time period, as we have already said that this two mass system can be reduced to a single mass of value mu, which is now connected with the same spring of constant k. We know how to find out the time period of oscillation of such a system, right? We already have this basic formula, T is equal to 2 pi root of m by k, which is for a mass m which is oscillating with a spring constant k. This will now reduce to 2 pi root of mu by k, right? So, we can just substitute the value of mu here, 2 pi root of m1 m2 over m1 plus m2 times k will be the final answer. Simply, so you do not have to do anything here, just consider the reduced mass system and find out the time period. Next set of application is for a question where you have a small block kept over a wedge which is movable on the surface on which it is kept is absolutely smooth, and there is no friction between the block and the wedge as well. And this block small m is given an initial velocity v, and you are supposed to find out the maximum height h to which the block will reach on the wedge. Now, when you try to do this problem using reduced mass, understand that a few things here, that the moment when the block reaches the highest point, we know that its vertical velocity will go to 0, yes, but along the horizontal the system will still be moving. Yes, we know this from the basics, that as the block moves over the wedge and as it reaches at the curved surface of the wedge, it will continue to exert a normal reaction on the wedge at any point in time. Perpendicular to the surface of the wedge, it will be creating a normal reaction which will make the wedge move along with the block. Yes, and at the moment where the block is at rest with respect to the wedge, both the block as well as the wedge will be moving with the same speed along the horizontal, because they are in contact with each other at all the time at that point also. So, once we understand that the horizontal velocity of small m will be the same as horizontal velocity of capital M at the moment when the block reaches its highest point, we understand that V relative will go to 0 at this point. Yes, and once we understand this, we can now use the reduced mass concept to get the value for h here very easily by once again using the conservation of energy, writing the initial kinetic plus potential energy, which in this case will be half mu. So, right now I am just eliminating the capital M VCM squared term in kinetic energy, because I know it is going to get cancelled, because once again there is no external force here on the system. So, the velocity of center of mass will be a constant. Yes, and I know that this will cancel out on both the sides when I write the kinetic energy term. So, I will directly start with the reduced mass energy term, half mu into the relative velocity of the two, which is v minus 0, v for the small block, for the wedge the initial velocity is 0. So, this is the first term that we get. In kinetic energy, the potential energy here is 0. So, 0, this is equal to, on the right side when the block reaches a height h, it will have a potential energy of mgh, plus understand that now this term which is half mu into v relative will become 0 now, because v relative is 0 at this position. So, this term is 0 and we already have only one term on the left side. So, see that we can easily solve this equation to get the value of h. One single equation this time is giving you all the answers, otherwise you use two equations here, law of conservation of momentum and then conservation of energy. But see how the reduced mass system is helping you get your answer in one single equation, and hence making you save a lot of time during the exam. Next example, that we can work on this same lines to find out the work done by friction. So, the question here says that we have this block small m which is kept on a block capital M, which itself is placed on a smooth surface, horizontal surface, but there is a coefficient of friction mu between the two blocks, and you provide an initial velocity now to the block small m over capital M. And the question says that when block small m reaches the other end of capital M, it is found that the two blocks have the same speed at that time. And then you are supposed to find out the work done by friction during the process and also the loss of energy. Okay. So, if we try to do this question from the reduced mass system, reduced mass concept, see that once again, since this bigger block is kept on a smooth surface, we understand that the external force on this system is 0. Friction that is acting between the two blocks will become an internal force if we consider both the blocks together. So, this means the velocity of center of mass is going to remain a constant, which means I do not need to consider the kinetic energy of the center of mass term when I am trying to write the energy expression here, right. This time, but I know that I can't use the law of conservation of energy because friction is acting on the system and is doing some work, and friction, the work done by friction, because we know friction is a dissipative force, the work done by friction will essentially amount to a decrease in the overall energy of the system. But I can still use something like change in kinetic energy is equal to work done by friction, the work energy theorem I can still use, right. So, I can use change in kinetic energy, I can first find out, right. So, can we say change in kinetic energy in this case, which will be, let us say we are trying to find out the initial kinetic energy minus the okay, let us define the change as final minus initial only, final kinetic energy minus initial kinetic energy. So, final kinetic energy in the system will be when this block M has already reached here at the rightmost end, and we know that at this point both M and capital M will be moving with common velocity, let us say V dash, so that we understand that their relative velocity will be 0, right. So, when I try to write the kinetic energy term, finally eliminating the kinetic energy of the center of mass term altogether, because I know it is going to cancel out, I will get half of mu into V relative squared, which will give me a 0. This is the final kinetic energy of the system, right, minus the initial kinetic energy, which in this case is half into mu into V minus 0. Initially only small m has a speed V, capital M has no velocity. So, V minus 0 will be the initial relative velocity and square of this. Can we say by the work energy theorem, this change in kinetic energy should be equal to the work done by all the forces that are working here, and we see here, we have already observed that the only force working here is friction. So, can we say this is the value that we will get for the work done by friction? Yes. And do we also see that it is also the loss of energy by the system? Because all the loss of energy that is happening in this system is on account of friction doing work. So, whatever work friction does, all that work is dissipated in the form of heat or whatever form of energy it is dissipated in, it will be dissipated, it will be lost. Yes. So, this value of work done by friction that we get, by the way, this will be with a minus sign here. We know that the work done by friction will be negative here, yes, because as we see here, friction is acting in the forward direction, in the backward direction on small m, whereas the block will be moving in the forward direction. So, the work done by friction will be negative by it, though there will be some positive work done by friction on capital M, but we can find it out, we can actually calculate and find out that the work done by friction on small m will be greater, negative work done by friction on small m will be greater than the positive work done by friction on capital M. So, that the effective, the net work done by friction comes out to be negative itself. So, see that this itself is the loss of energy also. Yes. So, once again one single equation is giving you the answer for this question. One more example. This time we see the application of reduced mass in the questions related to gravitation. So this question here is m1 and m2 are two masses which are separated initially by a distance r1 from each other, and under their mutual gravitational attraction they start moving towards each other, and at any point in time when they are at a separation of r2, we are supposed to find out the relative speed of the two particles, two masses m1 and m2. Okay. Once again, since the question asks us to find out the relative speed, we understand that it becomes quite easy if we use the reduced mass concept here directly. One single equation once again, yes. Since gravitation is a conservative force, we can use the law of conservation of energy this time. So, since we know then that the net external force on this system is 0, considering m1 and m2 as a single system, velocity of center of mass is going to be a constant. So, I am not going to consider the kinetic energy of the center of mass term on both the sides. I will directly start with the kinetic energy of the reduced mass term. So, initially when the two masses m1 and m2 are separated by a distance r1 and they are at rest, right now they are at rest from, right, it is from this position that they start moving towards each other. So, can we say that the kinetic energy of the system will be 0? Half mu into V relative itself will be 0 because both of them are at rest. So, initial kinetic energy will be 0, but there will be a potential energy here, which we know the formula will be minus G m1 m2 by r1. Now, by law of conservation of energy, this must be equal to the final kinetic energy, which we can assume to be half mu into V relative whole squared, because we know we get a term containing V1 minus V2 over here, where V1 will be the velocity of m1 at this point and V2 will be the velocity of m2 in the opposite direction. V relative will be V1 plus V2 actually, but that will be V relative, right. So, I can directly write V relative here instead of V1 minus V2, and then the second term here will be corresponding to the potential energy, right. So, it will be minus G m1 m2 by r2. So, see that one single equation here is giving us the relative speed of the two particles. We can just solve this equation to get our answer. A similar application of reduced mass comes in electrostatics also, because of the similarity in the nature of forces that we have in gravitation and electrostatics. So, let us look at one question from here also. The question says there is this mass plus q, positive q charge with a mass m, which is placed at a point initially, but it is free to move, it is not tied with anything, it is not a fixed particle. And then there is another charge plus q with the same mass m, which is projected from infinity close to this charge, not really close to it, it is projected towards the other charge. And we understand that as this plus q will approach the other plus q, there will be a electrostatic repulsion between the two, because both of them are positive. And with time, what happens is that this charge plus q, which is approaching the other plus q, will slow down. Also understand that because the first plus q charge is free, it is not tied anywhere, this will also start moving towards left because of the same repulsion, yes. And the moment they are at the closest distance from each other, that will be the point when both the masses, both the charges will be at same speed. They are both moving with the same velocity in the same direction, yes. So, their V relative will be 0 at the distance of closest approach, which we can call as d, let us say, okay. So, if we just assume that let us say this plus q charge has reached somewhere here by the time, and the other plus q has already moved a certain distance to the left, so that we understand that the distance between them is this, the moment when both of them are moving with the same velocity v towards left. We are going to use the law of conservation of energy between their initial state and their final state, the state where they are at the closest distance, right. So, conservation of energy once again. Again, considering the kinetic energy of the initial system, it will be only because of the plus q charge which is being projected. So, it will be half mu into V minus 0 whole squared plus what is the potential energy of this system initially? Initially the two charges are separated by an infinite distance, so there will be no potential energy 0, is equal to the kinetic energy at the moment when they are at the closest distance of closest approach. We know that since both of them are moving with the same speed, the V relative term here will go to 0. Yes. Plus, if we are assuming here that they are at a distance of d from each other at that moment, can we say the potential energy that they have will be k q squared, q into q by d. And do we see once again this one single equation is helping us get the value of d just by solving it? Yes. So, see, this is how we have various applications of the reduced mass system. You know, otherwise you will do all these problems writing two equations, one for conservation of momentum, the other for conservation of energy or the work energy theorem. Every question involves a case where either you have the two masses which are interacting with each other but there is no external force, yes, or there is a system of two masses which are still interacting, they have a force which is dissipative in nature but that is an internal force. There is still no external force there, right. See that in both the cases we can use the reduced mass system to simplify our questions, right. So, students, I hope that you liked this video of today's. If you like the video, you please let me know. You can make your comments in the comment section, and you can let me know if you want me to take up some other topic like this, where I would take up the topic, the basic theory, and then we will see where all it can be applied. Okay. Do share this video if you find it helpful with your friends also, and consider subscribing the channel as well. Till we meet next, thank you and goodbye all of you.